Hi, everybody. It's Professor Mitchell, continuing with Chapter 8. The next integration trick for our bag of tricks is integration by partial fractions. This is used on rational functions. And I see that this was the point in the semester when I first made these where I discovered this PowerPoint template. All right. So as an introduction, let's talk about how would you evaluate this integral, the integral of 2 over x plus 1 plus 3 over x minus 3. So that is a very easy integral to evaluate. Let's just go over it real quick. All right, so I would break these into two separate integrals. I'm not going to actually physically do that, but think of them as two separate integrals. And they both have the form du over u. There's really no point in doing this u substitution. For example, if you let u equal x plus 1, then du is just dx. All right, so even easier than a baby u substitution. I'm just going to write the answer. This would be 2 times natural log absolute value x plus 1 plus 3 times natural log absolute value x minus 3 plus c. Easy, easy, easy. So now suppose I asked you to evaluate the integral 5x minus 3 over x squared minus 2x minus 3. So let's make that a little practice problem. You can pause the video and work on that and then come back and we'll compare notes. And I'll give you a hint, don't spend too much time on this. All right, so having tried that integral, did you nail it? Did you have trouble with it? Well, if you had trouble with it, I find that hard to believe because we just did it. And by the way, I'm teasing you right now. But let me show you what I mean. If I go back to the tablet, all right, here's the integrand from the first example we did, 2 over x plus 1 plus 3 over x minus 3. If I add those fractions together, this is a good Math C problem. Look what it comes out to when you add those fractions together. It comes out to 5x minus 3 over x squared minus 2x minus 3. So I told you, you just did it. All right, but the problem is, how do we take this and turn it into this? So a whole, well, not a whole chapter, but a good part of a chapter in Math C is turning this into this. So how do you run that backwards? And that's going to be a big part of this section. You may have covered this in a pre-calculus class. I do not cover it in pre-calc. I would love to cover it in pre-calc. I just have too many other things to cover. But turning a rational expression, and by the way, if you're rusty on your terminology, a rational function is the quotient of two polynomials. It's a polynomial over a polynomial. So how do you turn a rational function like this into little pieces like this that you know how to integrate? Well, you do that using a method called partial fractions. So I'm going to, so first I need to share this fun fact with you. Every polynomial with real coefficients, I don't care if it's degree 3, degree 4, degree 11, can be factored into linear and irreducible or prime quadratic factors that all have real coefficients. And that's kind of an amazing fact. So what that means is, let's say that you have a polynomial of degree 11, and somehow you're able to break it down into two factors that have degree 8 and degree 3. So what this fun fact says is that you can break both of those down further. you can, and every time I say can, I put a little star next to it, break that thing down into a bunch of factors that are no bigger than degree 2. Okay. So the star means that these factors may be difficult to find in practice, but they do exist. All right. But don't worry, all the examples that we're going to go over in this lecture and all the examples in your homework, you will be able to factor them. Okay, if they're not already factored. I think most of them are already factored. Okay, so here is the sort of big scary presentation of the method of partial fractions, and then I'm going to translate this into English for you. So the first thing I want to direct your attention to is at the very top in blue, it says that f of x over g of x has to be a proper rational expression. In other words, the degree of f of x has to be strictly less than the degree of g of x. So the first thing I want to tell you is that if I hand you a rational function and it's not proper, the very first step you have to do is long division in order to rewrite it in a form that involves a proper rational expression. Okay. So step 1 is to check the degrees and do long division if necessary. Okay. All right. Now steps 1 and 2 are what I'm going to translate into English for you. And I think I'll just go ahead and do that. I've done that on the tablet. So let's, let's look at the tablet. All right, so the first case to consider is when the denominator of your rational expression has nothing but linear factors. So in this example, I've got, nothing but linear factors, okay? 3 different linear factors, x plus 1, x minus 2, and x plus 4. So in this particular example, the way that you would break up this rational expression is like this. You take the first linear factor, which notice is to the first power, and you write that as a over x plus 1. Then the second linear factor has degree 2. So what you have to do with the ones that have exponents on them is to sort of count up. So you start with that linear factor to the first power, and then go second power, third power, fourth power, etc. And then finally do the same thing with x plus 4 over 3. So that requires 3 separate terms. Okay. And then we'll talk in a little bit about basically what you have to do next is solve this equation for A, B, C, D, E, and F. All right. Okay, now what do you do if there are irreducible quadratic factors? What do I even mean by irreducible? Well, irreducible means, like in the case of x squared plus 1, there is absolutely no way to factor that using real coefficients. The only way I know to factor x squared plus 1 is with imaginary numbers. It's x plus I times x minus I. So we're not interested in I for this. It has to be real numbers only. So if you have quadratic factors that cannot be broken down into linear factors, like in this case, x squared plus 1 and x squared plus 4, this is how you have to break them up. So first I have the x squared plus 1 to the first power. All right, so the big difference between this and the linear factors is that you use something like an ax plus b instead of an a. You use a mystery linear expression instead of just a mystery number, okay? And then you do the same thing if you have exponents that are higher than 2, you count up and put a mystery numerator of the same type on top of each one. Okay. All right. So those are the possibilities. By the fun fact, all of the factors have to be either linear or irreducible quadratic. Okay, so let's briefly look at numbers 3 and 4 here. You're going to set the original fraction equal to the sum of those partial fractions, and then clear the resulting equation of fractions. And actually, I am going to do this a little differently than they describe it here. I think my way is a little easier often, not always, but at least half of the time. All right. So that brings us to our examples. So we're going to go over 4 examples. Some of these are going to be a little time consuming, but let's just get started with the first one. All right, letter A. We have the integral from 1/2 to 1 of y plus 4 over y squared plus y dy. So the first thing you have to do is rewrite that rational expression using the method of partial fractions. So first of all, notice that y squared plus y factors into y times y plus 1. All right, so those are 2 distinct linear factors. So what I need to do now is find the mystery numbers a and b that make y plus 4 over y times y plus 1 equal to a over y plus b over y plus 1. All right, so the first thing I'm going to do is multiply both sides of that equation by y times y plus 1, and that's to get rid of the fractions. Okay, so on this side, the y's cancel, the y plus 1's cancel, and that leaves me with y plus 4 equals. Now I'm going to distribute the y times y plus 1, a over y times y plus 1. The y's cancel and leave me with a times y plus 1. And then distribute it here. The y plus 1's cancel and leave me with b times y. Okay. All right, so here's where my method differs a little bit from what the book tells you to do. So keep that in mind when you use show me an example. It's going to do it a little differently. All right, I am going to, so this equation that you see here has to be true for all values of y, all values of y. So what I'm going to do is carefully select some values of y that are going to make this equation a lot simpler and make it pretty obvious what a and b have to be. And the best way to choose these values of y is use values of y that will make whole entire terms drop out. For example, if I use y equals 0, that's going to make that term drop out, and it should tell me exactly what a is. So setting y equal to 0, that gives me 4 equals a times 1 plus 0. Oh, I think I know what a is. I think a has to be 4. All right, so what would be another good value of y to make a whole entire term drop out? Well, how about y equals -1? We'll make this whole entire term drop out. Okay, so on the left side, I'm sorry, I have -1 plus 4 is 3. And then I have a times 0 plus b times -1, right? So that equation says 3 equals -b. which means b is -3. All right. So here's what we have. We can now take our original integral, the integral from 1/2 to 1 of y plus 4 over, I think I'll write the denominator like this. No special reason. Okay, and that becomes the integral from 1/2 to 1 of, let's just make sure it was a over y, and a is 4, so 4 over y minus 3 over y plus 1 dy. All right, and this is exactly the same kind of integral that we did at the very beginning. This is going to be, and by the way, y is positive in the interval from 1/2 to 1. So I'm not going to bother putting the absolute value. Normally I would say 4 natural log absolute value y. In this case, we can just say y, because we're not going to be plugging any negative numbers in there. Minus 3 natural log y plus 1. Plug in 1, plug in 1/2. And what we get is 4 natural log 1 minus 3 natural log 2 minus 4 natural log 1/2 minus 3 natural log 3/2. All right, so let's see how much we can pretty this up. Natural log of 1 is 0. So we have -3 natural log 2. And now, oh, let's distribute the minus sign. So then, well, actually, let's do this. Natural log of 1/2 is equal to negative natural log 2. Remember that was a property of logarithms. Okay, so I think that's what I'll do with that. I'll just rewrite it as -4 natural log 2. So when I distribute the minus sign, that's going to give me plus 4 natural log 2. And then plus, okay, this thing I'm going to rewrite using the quotient rule for logarithms. Instead of natural log 3/2, I'm going to write it as natural log 3 minus natural log 2. You know me, I'm just trying to make the answer look as pretty as I can. All right, so we have a whole bunch of natural log 2's. We have -3 natural log 2 plus 4 natural log 2, and then we can tack on another -3 natural log 2. So -3 plus 4 is 1. 1 minus 3 is -2. So I think we end up with 3 natural log 3 minus 2 natural log 2. And I think that's how I would leave the answer. I've said it before and I'll say it again. If you don't want to pretty up your answer quite as much as I do, your online homework has a pretty open mind about what form the answer goes in.